Okay, let's have a look at these questions for moments. So question 1, AB is a uniform rod of length 5 meters and weight 20 newtons. In these diagrams, AB is resting in a horizontal position on supports at C and D. In each case, find the magnitudes of the reactions at C and D. Okay, so for this question here, it's the same method for all of them. So we start with the beam. For question 1, it's going to have a point C, and then at D, and then we know the distances, so it's 1 meter between the edge and C, it's 3 meters between C and D, and it's 1 meter from D to the end. And we know that the weight is 20 newtons, so that means when you have a weight on it, it acts in the middle of the beam, exactly halfway. So this is 20 newtons, and this is 2.5 meters from either end, because it's halfway in the beam, and the beam is 5 meters. So the first thing we need to notice is that they should be in equilibrium. Yeah, it's resting in, we're assuming that it's going to be in equilibrium, it's resting. So the first thing we can say is just saying that the upwards forces equals the downwards forces. So the upwards forces, we've got the reactions at C and D. So these forces go upwards as the C and D are acting upwards on the beam, supporting the beam's weight. So therefore, when we plug it into here, it's going to be C plus D, which are acting upwards, which is equal to 20 newtons going downwards. So we're going to come back to this formula later on. Then the second one is the principle of moments, which is anti-clockwise equals clockwise. For this one, we need to pick a position for the moment. So here we're going to pick C. So we're going to take moments from C. So moments from C. So when we take moments from C, you need to determine which way the forces acting on the beam are going. So the way that I think about it is imagine that you are standing on the beam and then thinking about how do the forces go around you. So the 20 Newton force will go clockwise around you. You're at the center of the clock and the 20 Newton force is going down. So if you hold your hand, your left hand out, if you're standing on the beam, then that would go round you. So here in the clockwise direction, it's going to be 20, and then going in the opposite direction is D, which is going anti-clockwise, so the D is going clockwise. So that tells you the direction. We need to use our formula. So the formula for moments is force times distance. So the key thing here is that it's distance from the point where you're taking moments from. So if we look at D to start with, this is 3 meters away from C. So therefore it's going to be 3 times D, and that's equal to, so that's the anti-clockwise moment again. Anti-clockwise equals clockwise. Then we need to find the distance to 20 newtons. So C is already 1 meter away. We know that this distance here is 2.5 meters. We've already travelled 1 meter, so to fill the rest of it, it's going to be 1.5 meters from C to the middle of the beam. So it's going to be 1.5 times 20. And then from here, we just do a simple rearrangement. D is equal to, so D is equal to 1.5 times 20 divided by 3. Plugging that into our calculator gives us an answer of 10. So D is equal to 10 newtons. Now it wants us to find C as well. We know already that the upwards forces must equal the downwards forces. So now we go back to our equation C plus D is equal to 20, and we plug in D. So it's going to be C plus 10 is equal to 20. So C is equal to 10 newtons. And that's your answer to question 1. If we look at, or 1A, if we look at 1B, so it's going to be a similar method as before. So again, we're going to just shortcut it slightly. So C and D, and this time the key thing that we need to find is the weight point here is 20 newtons. Now here the difference is obviously the distances between each of the parts. So again, we know that the reaction force at C is going upwards and the reaction force at D is going upwards. So it's going to be up equals down. So C plus D is equal to 20. Again, we're going to take moments. We could take moments from C. So anti-clockwise equals clockwise. Again, 20 newtons is going clockwise around C, D is going anti-clockwise around it like a clock. So it's going to essentially be D is on that side, 20 on the other side, and then we take moment, which is force times distance. So we're going to take moments from C. So D, now if we look at D, there's a clear one here, it tells us it's 2 meters away. So it's going to be 2 meters here. So on the left hand side, it's going to be 2 times D. And this time we need to look at 20, where we know that this distance here is 2. This is always, the weight is always halfway, so it's at 2.5. So this distance here must be 0.5 meters, and therefore we get 0.5 times 20. And then from here we just do a simple rearranging. D is equal to 0.5 times 20 is 10, 10 over 2, so D is equal to 5 newtons. And then we plug that back into our original equation. So C plus 5 is equal to 20, so C is equal to 50 newtons. For part C, we have, again, a similar method. So C is going upwards, we've got the weight going downwards, and D is going upwards as well. This here, 1.5, we know that this distance here is 2.5, therefore, again, using the method that we know, this distance here is 1 meter, and this is 1 meter to the end. So in this case, again, we're just going to pick, this time we'll stick with the same one that we got. So up equals down, so C plus D is equal to the weight. Again, the weight is always going to be 20 newtons, so C plus D is equal to 20, and then anti-clockwise equals clockwise. Again, the weight is going this way round your C, so from the point where you're taking moments from, so moments from C, so here it's going to be weight, and D is going anti-clockwise, around C. And then we use our formula, so moments equals force times distance. D this time is 2.5 meters away, so it's going to be 2.5 times D is equal to, and this time, as it's 1.5 meters away from the edge, C is 1 meter away from the weight, so it's going to be 1 times 20. So D is equal to 20 divided by 2.5, and therefore we plug it in to give us 8 newtons. When we then plug this back in, so here it's going to be C plus 8 equals 20, so C is equal to 12 newtons. And that's our answer to part C. And then part D, let's change it slightly. So this time we're going to take moments from D. So let's draw out our one. Again, you don't have to do this, you can always take moments from C, but let's just see it in a slightly different format. So here is 1.5 meters. We've got C going up. We know that this distance is 2.7 meters. We know that the weight is acting in the middle, so that's 20 newtons, and that distance is 2.5 meters. And we know that this is 0.8 meters. Okay, so again, do our force at D. So up equals down, C plus D is equal to 20. And then we take our moments. So this time we take moments from D. So if we take moments from D, the weight force this time, so remember clockwise equals anti-clockwise, anti-clockwise equals clockwise, same idea. So this time for the weight is going anti-clockwise around D. Remember, you take D as the center, and then you work out which way is your force. So essentially draw your force around D, and this time C is clockwise. And then from here we use our formula, moments equals force times distance. So in this case here we're going to have, so the weight here, we're 0.8 meters away from the edge, and we know that the distance from the weight to the edge is 2.5 meters. So here we just need to do 2.5 minus 0.8, which is 1.7. So the weight is 1.7 meters away and it's 20 newtons, so that's the distance and the force. And C is given to us as 2.7, so it's 2.7 C. And then from here we just rearrange, so C is equal to 1.7 times 20 divided by 2.7. And then from that one gives us a horrible answer actually of 340 over 27, which to three significant figures is 12.6. But all the time use the actual answer when you're calculating the next part. So we know that C plus D is equal to 20, so D is equal to 20 minus 340 over 27, which gives us an answer of 200 over 27. And that gives you your answers for question 1. Question 2, each of these diagrams show a light rod in equilibrium in a horizontal position under the actions of set forces. Find the value of the unknown forces and distances. So if we assume it's a light rod, we're going to assume that there is no weight on the rod. So from here we don't have to worry about the weight. In here we're just going to focus upon the forces that are acting on it. So again, similar idea in terms of, so for question 1, up is equal to down. Here is going to be x plus y, both those forces going up, and then going downwards is 10 plus 15. So x plus y is equal to 25. Then we're going to take moments. So let's take moments from x. So if we take moments from x, we need to determine the way in which the forces go round x like a clock. So imagine that this is the centre of the clock. So we know that the principle of moments, anti-clockwise equals clockwise. So the 10 is going anti-clockwise, the y is also going anti-clockwise, and the 15 is going clockwise. So again, feel free to draw on your diagram to know which way the forces are going. Then we do our formula, which is moments equals force times distance. So if we look at the anti-clockwise ones, first of all we've got 10. So 10 newtons is 1 meter away from x, so it's going to be 10 times 1. And then the next one that we have is we have y, so we're going to add that moment on. So this is 2 meters away, so it's 2 times y. And this is equal to the clockwise one, which is 15, and this is 2 plus 1 meter away, so it's 3 meters away times 15. From here we just do the algebra, so it's 10 plus 2y equals 3 times 15, which is 45. So 2y is equal to 35, so therefore y is equal to 17.5 newtons. And then from here we then don't need to solve the other moment, we can just plug into our equation. So x plus 17.5 is equal to 25, so 25 minus 17.5 is 7.5. So x is 7.5 newtons. Look at question 2. So question 2 is a different setup this time. This time we've got x is going downwards, y going upwards, 15 newtons and 20 newtons. So from here, our up and down is going to be different. So it is indifferent in terms of we've got unknowns on both sides. So here going upwards is 15 and y, and going downwards is 20 and x. So it looks like a times. So it'll be 20 plus x. And then we're going to take moments. So we get anti-clockwise equals clockwise. From here you can take moments from any. I usually take it from the end if possible because that makes it simple. So we're going to take moments from x, but you can take it from any side. So if we take it from moments from x, y is going round clockwise, 15 is also going round clockwise, and 20 is going anti-clockwise around. So then from here we use our formula, moments equals force times distance. So 20 is at the end, so it's 1 plus 2 plus 1, so that's 4 meters away. So it's 20 times 4 is equal to y. Y is 1 meter away, so it's just going to be 1 times y. And then we add our next moment, so this is 1 plus 2, so that's 3 meters away. So 3 times 15. From here we've got 80 equals y plus 45, and then we subtract 45 away from 80, so 80 minus 45 is 35, so 35 is equal to y. From here we then go back to our formula, our up and down, our vertical forces. So it's 15 plus y we found is 35 is equal to 20 plus x. From here we just then do the algebra, so 15 plus 35 is equal to 50, so 50 equals 20 plus x, so therefore x is going to be 50 minus 20, which is equal to 30 newtons, and y, make sure you put the correct symbol, so it's 35 newtons for y. For part C, leave that one for that one. So for part C here, we've got the introduction of G. So G here is 9.81, although usually I keep G until the end. And in this case here, we're going to be careful because we've now got an unknown distance, which is D. So from here, again, always to start from the following, up equals down. So the upwards forces are 5G plus x, and this is equal to 5G plus 10G plus 15G. I am assuming that G is gravity in this question. I don't have the context of it. I assume that that's what it's meaning. So from here, we are going to take moments. We take moments from the unknown force, which is x. So we do anti-clockwise equals clockwise. The reason why we take it from x is we don't know what's happening at that point. So again, we go through. So going clockwise is the 15G. Going anti-clockwise is 10G. Going clockwise is 5G. And going anti-clockwise is 5G. So here, moments equals force times distance. So first of all, we start from the 5G at the end. So 5G times, so it's the end 5G. So 3 plus 2 plus 2. So that's going to be 7 plus 10G. Now the 10G is here, so that's only 3 meters away. And then we look at the clockwise forces. So we've got 15G. Now 15G is multiplied by D. So it's going to be D times 15G. And then we've got the last one, which is the 5G that goes around, so that's 5 meters away. So plus 5G times 5. From here we can simplify, so it's 35G plus 30G equals 15GD plus 5 times 5 is 25G. We've now got a common factor of G in each of the terms, so this can be cancelled out. And now we're well on our way to finding what D is. So here 35 plus 30 is 65, that's equal to 15D plus 25, and then we move the 25 to the other side, so 65 minus 25 is 40. So 40 equals 15D, 40 divided by 15 is 8 over 3, so D is 8 over 3. Also, I didn't realize at the start we actually found a moment, but we could also find our unknown value straight away, simply because we can just rearrange this equation. So I missed that you could have easily solved this one straight away. If we move 5G to the other side, we end up with x is equal to, these 5Gs will cancel because 5G minus 5G is 0, so x is equal to 25G. Yes, I didn't realize, yeah. So that's how you solve this question. So a little bit more trickier. Question. Then we've got the last question. I am going to remove, about to clear everything out of the way for our last one. And then we're going to look at part D. So part D, we have got actually several unknowns here. 2 unknown forces and 1 unknown distance. so we start off with up equals down. So upwards is 2x plus 3x, and that's equal to 5g plus 10g plus 10g. So that gives you 5x is equal to 25g. So x is equal to 5g. That's very straightforward one. We didn't need to do moments there. And then for the next part that we have is we need to take moments. Again, I'm going to take moments from the 2x. You can take moments from any of these points actually to find what d is. So actually, at that point I'm going to make it my life a little bit simpler for moments. I'm going to take it from the 5g. So moments from the 5g. As we found our x value, we can actually solve it from here. Now the reason why I'm doing that is because it makes it very simple when we're measuring our distances and also our directions of moments. So here, if you've not noticed already, if you take it from the end, all the upwards forces go in the same direction of moment. So in this case, anti-clockwise. So we've got 2x and 3x, and below we've got 10g and 10g, both going in the same direction. Make sure you put both 10g's in because they're different distances away. Now here becomes a little bit algebraic. Actually, so at this point here, I realised that it would be easier because of this d is going to be in every single turn for our distance. So in this case here, and in the exam you might find this, it might be better to stop rather than just using the sunken fallacy idea of continuing. If you can see a quicker method, then stop and use that method. So here I've realised that actually, this is just mainly from experience, it's actually better to start from here. Now the reason why it's better to start from here is that I've only got one d to solve. Every other distance doesn't involve a d. While if I started from here, I've got to have d in every single one. It's d plus 1, d plus 1.5 plus 1, d plus 1 plus 1.5 plus 1, which makes my algebra a bit more difficult at the end. So if I take 2x here and I do moments from here, this time I'm going to have a little bit of an easier ride. Again, you could have solved it either method, you could have started anywhere, etc. But I believe that this method is one of the quickest ways of doing it and less likely to make a mistake. So here, again, this time you've got to be careful because 5g is going anti-clockwise, but 10g is going clockwise. So you just need to be careful that, again, your downwards forces are going in different directions depending on the side it starts on, and 3x is going anti-clockwise. So then from here, we're going to measure our distances. For again, moments equals force times distance, so it's going to be 5g times d, and then plus 3x, and 1 plus 1.5 is 2.5, and that's equal to 10g, which is just 1 meter away, so 10g, plus our second 10g, which is a bit further away, 1 plus 1.5 plus 1, so 1.5 plus 2 is 3.5. From here, now we are going to solve, so it's 5gd is equal to 3, now 3x here we know is 5g, so it's going to be 3 times 5 times 7.5, no sorry 2.5, my mistake, that's my handwriting, I apologise, so just 2.5, and that gives you 37, that is not equal to, it's plus 37.5g, that's equal to 10g plus 10 times 3.5 is 35g. From here we rearrange, so let's get everything over to the right hand side, so it's 35 plus 10 minus 37.5, so that's 7.5g. We can immediately cancel the g's, or we could have done this before, but cancel the g's, we're left with 5d equals 7.5, so then 7.5 divided by 5 is 3.2. So d is equal to, it's not 3.2, 3 over 2, which is 1.5 meters. And that gives you your answer to part D. Question 3. Jack and Jill are playing on a seesaw made from a uniform plank AB of length 5 meters, pivot at M, the midpoint of AB. Jack has a mass of 35 kilograms, Jill has a mass of 28 kilograms. Jill sits at A. Where must Jack sit for the plank to be in equilibrium when horizontal? Okay, so we're going to play seesaw is like this. We assume, again, equilibrium when horizontal. It's got a length of 5 meters, so we know that the whole thing is 5 meters. Pivoted at M, so M is the midpoint, so we're going to assume that there's a midpoint here, and there's going to be a reaction force at that point. Jack has 35 kilograms, so at A is here, and Jack is sat at some point here at 35 G. Again, that's the mass, so the weight that he's acting is 35, and he's going to be some distance A from the plank, from the centre of the plank, and Jill sits at A, so Jill is sitting right at the edge here, and she's got a weight of 28 G. Where must Jack sit for the plank to be equilibrium when horizontal? Okay, so again, it's in equilibrium, so we know up is equal to down. The upwards force is R, and the downwards forces are 35G plus 28G. But do we need that? Doesn't help us yet because we want to find this distance here, A, or little a, or we can change that to a D. So D is our distance from the centre of the plank. Now here we have now found R, technically it's just 35 plus 28G, but I'm going to take moments from R because originally it was R unknown. So take moments from R. We take moments from R, we've got anti-clockwise and clockwise. So we've got 28G, which is going anti-clockwise, and we've got 35G, which is going clockwise. Then we find the distances. The pivot point is halfway, so this is 2.5 meters. So it's going to be 28G times 2.5. And 35G is D meters away, so 35G times D. And then from here we just plug in our numbers. So it's going to be 28 times 2.5, which is 70. So 70G is equal to 35GD. If we divide both sides, so 75 divided by 35 is equal to 2, and the G's cancel, so 2 is equal to D. So therefore, he has to sit 2 meters away from the 2 meters away from the center point. This question is not super clear because usually it tells you where must Jack sit, so that doesn't really clear. So as long as you make it clear when you set up your question what you're looking for, that should be fine. In the exam question, it will be a much clearer where is Jack, where is the position he's sat from. Here we've just assumed it's from the centre. A uniform rod AB of length 3 meters and mass 12 kilograms is pivoted at C, where AC equals 1 meter. Calculate the vertical force that must be applied at A to maintain equilibrium with the rod horizontal. So again, this is a flat rod. This length here is 3 meters. It has a mass of 12 kilograms, so we know that there's going to be 12G in the middle. It's pivoted at C, so this is A, this is B. AC is 1 meter, so there's a pivot at this point here, which is 1 meter, and that's C. Calculate the vertical force that must be applied at A. So there's a vertical force here at A to maintain equilibrium with the rod horizontal. Okay, so here there is also a reaction force at C. So we need to solve this, so it's going to be A plus C is equal to 12G, and that comes from the upwards forces equals the downwards forces. We're then going to take moments, so we've got two unknowns here. We've got an unknown at C and an unknown at A. We simply want to find what A is, so we're going to take moments from C because we don't know what C is, and therefore taking moments from there will get us our answer to A directly because we need to plug in A. So first of all, we're going to do anti-clockwise equals clockwise, so 12G is going clockwise and A is going anti-clockwise. Then we do our formula, moments equals force times distance. So now we're taking it from C, so A is 1 meter away. So it's simply just going to be A times 1 is equal to 12G. And then we need to find how far 12G is. Well, we know that the halfway point is 1.5 meters, and that's where the weight is acting. We know that it's already travelled 1 meter, C is 1 meter away from the edge, so therefore this point here must be 0.5 meters. So it's going to equal 12 times 0.5. And then from here we solve, so A is equal to 6g. So that gives you the, so that gives you the vertical 6g. If they want it to several significant figures, we do 6 times 9.81, which gives you an answer of 58.86 newtons. If we take g, it's 9.81. A broom consists of a broomstick of length 130 centimeters, mass of 5 kilograms, and a broom head of mass 5.5 kilograms attached at one end. By modelling the broomstick as a rod and the broom head as a particle, find where a support could be placed so the broom will balance horizontally. Okay, so this one, it's quite a more challenging question than what we've seen before. So this one, we've got a length of 130 centimeters. So the broomstick's length, that one, the weight will act halfway, so that's going to be 5 kilograms, so 5g, and a broom head attached of 5.5 kilograms attached at one end. So we're going to attach it from here, and this is going to be 5.5g. By modelling the broomstick as a rod, find where a support should be, where the rod is going to balance. So I'm assuming that the support could go here, but we don't actually know where it could be. So we're going to say this is a support A, and that force is going to go upwards here. And it's going to be D away from the edge of the rod. So again, a lot of these are assumptions. I don't know where A is. A could be all the way over here, as far as I know. But we're just going to say it's here. And the key thing here is we're saying D is from a particular position. So we're saying D is from where the broom head is going to be. Again, if the broom head is a particle, that means that there's no dimensions essentially to it. We're just going to assume it's just acting on the broom straight downwards. So then from here, once we set this up like this makes it a very straightforward moments question. So up equals down, so the upwards force is A, and that's equal to 5.5g, which goes downwards from the broom head, and 5g from the mass of the broom, so that's equal to 10.5g. So we found what A, the force of A, is going to be, but we're not interested in that. We're finding out where should the support be placed. So here we're going to find moments, so anti-clockwise equals clockwise. So where are we going to take moments from? Well, you can take moments, there's no point taking it from A, because you want to, or you could do, yes, actually you could take moments from A if you wanted to, and that's perfectly fine. So we'll take moments from A. In fact, that's the best choice, because it involves, you may have made a mistake here, for example. So if you try and avoid using any of your previous workings, if like big one for this one is Suva, it could potentially stop you from losing marks if you've made a mistake and you didn't realise. So here we're going to take it from A. And we're going to do anti-clockwise and clockwise. So again, anti-clockwise is 5g, clockwise is 5. Oh no, sorry. No. Sorry, that's a mistake. So obviously this one is going this way round. So 5g is anti-clockwise and 5.5g is clockwise. I drew the arrow the wrong way round. And then from here we just find our distances. So this one is, yes, so this one's going to be interested to find out distance. So the first one I'm going to do is actually 5.5g, because that's easy, that's d. So it's just 5.5g times d. The next one though is a bit more tricky, because we need to find this distance here. We know that this total distance is 130 divided by 2, because it's the weight, so it's acting halfway, so it's 65. We know that already that this has travelled d, so the remaining part of this is just going to be 65 minus d, okay, because we've already travelled that d, so we subtract that off 65, and that gives us our remaining distance between A and the middle of the broom. So here, when we do our thing, when we put it into our formula, it's 5g, 65 centimetres minus d. And from here, it just becomes an algebraic equation. We expand. So first of all, we can cancel with g's, so we don't have to do any more writing. And then we can expand the bracket out. So it's going to be 5 times 65, which is 325 minus 5d equals 5.5d. Move the d to the other side, so it's 10.5d, and then divide by 10.5. And that gives an answer of a horrible answer. 325 divided by 10.5 is, 650 over 21 centimetres. Always write out the fractional answer first, because then this one to 3 significant figures is 31 30.0 centimeters. It's 30.95, round that fourth significant, yep, so round it up. It's 31.0 centimeters from the edge. And because you've defined where D is in your diagram, you don't need to write anything else. And that gives you your answer to this question. The last question we have, question 6. A uniform rod of length 4 meters and weight 20 newtons is suspended horizontally by 2 vertical strings attached to A and at B. A particle of weight 10 newtons is attached to the rod at point C where AC is 1.5. Find the magnitude of the tensions in the 2 strings. Okay, so we're going to draw a uniform rod. So again, build up your diagram with the question. So length of 4 meters, got a weight of 20. So again, that's going to act halfway. So if you on big questions, it might just be worth putting that distance there so you remember what it is. And it's suspended between 2 vertical strings attached to A and B. So we know that the rod is A and B, so we know that there's a string here and there is a string here. So that one is A going upwards and that one is B going upwards. And then finally we're given a particle of weight 10 newtons is attached to the rod at point C where AC is 1.5. So AC is 1.5 puts it this side here. This is 10 newtons and this is 1.5. And our goal here is to find what is the tensions in the 2 strings. So to find out what that is, the first thing we do is we say that up equals down. So A plus B is equal to 20 plus 10. So A plus B is equal to 30 newtons. Then from here we take moments. So we can take moments from either A or B because we don't know them. So we're just going to take moments from A. So if we take moments from A, we do our work out the direction. So anti-clockwise equals clockwise. So 10, take it as a center. 10 is going to go round clockwise. 20 is also going to go round clockwise. And B is going to go round anti-clockwise. And then we do our formula, which is moments equals force times distance. So B, the rod, is a whole length of 4, so it's going to be 4 times B is equal to 10, which is 1.5 meters away, so 1.5 times 10, plus the halfway point is, so it's 2 meters, so it's going to be 2 times 20. From here, we just plug it in our numbers, so 4B is equal to 15 plus 40, so B is equal to 15 plus 40 divided by 4, so B is 55 over 4, which is equal to 13.75 newtons. And from here, we just plug in our, plug it back into our formula. So A plus 13.75 is equal to 30, and therefore A is equal to 30 minus 30.75, which gives you 16.25 newtons. And that brings the end of these questions. Any questions that you might have, please let me know.